For those who are here, today we see laboratory 3. Laboratory 3 is principal component analysis and linear discriminant analysis. So what we saw last week and yesterday. Today we will focus on the first part, what we saw last week, so PCA, and then this laboratory will also stay with us next week. So the text is for this and next laboratory. So this will be a 2 weeks laboratory. So it's long, you can see, but it's not meant to be finished today. Actually, today we have the shortest parts of the 2. Today we will focus on PCA and start to do those things that we can already do about LDA that don't require us to still understand exactly how LDA works, but we can already do with the definitions we gave yesterday so that we don't have everything about LDA to do next week, because LDA is already a bit more complex on its own. In any case, what do we do today? The first part is on PCA. For the moment, we use just PCA, and we see how PCA would transform the ARIS dataset when we use PCA, when we estimate the directions directly on the set itself. That is, we will take our ARIS data, estimate the PCA matrix from the ARIS dataset, and then we will apply this matrix again to the dataset itself. So the data we applied the PCA on is the same we trained the PCA on. Now, this is an exception to the rule that we will follow when we do classification. This will allow us to analyze what happens with PCA. Typically, our pipeline will involve using a training set to estimate the PCA matrix. Then this matrix will be applied to transform also the training set, but also to transform the data that we will evaluate our classifier on. What does it mean? It means that when we run classification, we said we have at least 2 data sets, the one we use to train the model and the one that we will use to evaluate our model. When we use PCA as a preprocessing for a classifier, and we will see this exactly in detail next week when we use preprocessing, PCA as a preprocessing for LDA, the training of the PCA will happen on the training data, but the same PCA matrix will we use to project both the training data to further learn a classifier and the evaluation data. When we project the evaluation data, we use the matrix estimated from the training data. We don't estimate a new matrix on the evaluation data itself, okay? So, we will see this in detail, but today, what we do today is not the typical use case. Today, we take the data, we estimate PCA, and then we apply this same PCA to the same data and see what happens. This is to say this will not be the typical pipeline when we do classification. We will explain in detail the pipeline tomorrow next week when we do classification with LDA after PCA. I just wanted to put this as a forward to say it in advance, to pay attention that what we do today is not the typical use case. But in any case, today we said we want to do 2 things: start writing a function that computes the PCA matrix from some data set with a given number of dimensions, and then we will want to do a function that, given the matrix P and some data, will apply the projection to this data. And in this case, the data will be, in this case, we will use the same data for in both these steps. So how do we compute the PCA matrix? To compute the PCA matrix, given some data, we need to compute the covariance matrix of those data, which means we start computing the mean of the data set. And then, given the mean of the data set, we compute the covariance matrix. Here you have the details on how to do it with the 4 loops or in an efficient way. These are the same steps that we saw in the last laboratory. If you have done the last laboratory, you already have a solution for these two steps, compute the mean and covariance matrix of a dataset. In case you didn't do those laboratories, here you have again the steps that you can follow. Let's say that if you did the previous laboratory, essentially all these parts you already know how to do. Otherwise, you have all the details. Next, once we have computed our covariance matrix, we said that to compute, and here you have the solution that you should obtain numerically so you can compare. Once you have computed the covariance matrix, we need to find the eigenvectors, the m leading eigenvectors. Here you have two possibilities. The first employs this function h, and this is another possibility I will discuss in a moment. The library h is a function that computes eigenvectors. You have two functions that compute eigenvectors, actually you have several. You have eig, that is a general function, and eig, which works for symmetric, well, it works for emission matrix. In our case, asymmetric matrix. Why is it better to use the latter? Because the first doesn't know that we have a symmetric matrix, so will give in general complex eigenvectors. Even when they are real, we may have values that are still represented as complex numbers, and that is not good for us. While the second function knows that for a Hermitian, well, in our case, for the symmetric matrix, let's simplify, the solutions are real eigenvectors. So it will directly compute a real values for the solution. So it simplifies our computations because it directly gives the specialized solution for this kind of matrices. The only issue is that it will give the vector of eigenvalues and the matrix of eigenvectors as columns of U, so it's coherent with our representation. The solution will be the columns of U. The only problem is that it sorts these columns in increasing value of eigenvalues. So the first column will be actually the eigenvector associated to the smallest eigenvalue. So essentially what we would like is to have the last m columns of this matrix in reverse order. One possible way is we take the matrix of eigenvectors and we reverse its columns using the slicing operation that reverses the columns, and then once we have done this, we take from the new matrix the first m columns. This will give us the m leading eigenvectors sorted by decreasing value of the eigenvalue. Another possibility is to use the singular value decomposition that for a semi-positive symmetric matrix as the covariance matrix corresponds to an eigen decomposition of the matrix. When the matrix is symmetric, semi-definite positive, that is, all eigenvalues are greater or equal to 0, and the matrix is symmetric, then SVD and eigenvector decomposition become, well, the SVD is one possible eigenvector decomposition of the matrix. So we can use this function. The benefit of this function is that it will give us the matrix of eigenvectors, of singular vectors, but in case these are the eigenvectors, in already the order that we want. So from the leading to the smallest eigenvalue, 1. So we can, if you use this second approach, we can just take the first m elements of matrix U, the first m columns. Then, once we have implemented in one of these two ways the estimate of P, we need to apply our projection. And in this laboratory, we said we apply it to the same iris dataset that we use, the same samples that we estimated on. How? Well, let's say that we have our data matrix S1 to Xn, then we want to compute the new data matrix obtained by projecting each of these points over P. For sample xi, the projection is P transpose xi for a generic sample. So I want to build the data matrix that contains all the projected samples. I can do that with a for loop over the columns of matrix D, or I can observe that I can build directly this matrix, let's call this dP. dP can be defined directly as matrix product between P and the original data matrix. Why? Because if I take a matrix and left multiply it by P transpose, that's equivalent to multiplying each of the column of the matrix by P transpose. Again, how do I prove it? It's a simple matter of writing the definition of matrix-matrix multiplication and see what happens when I multiply one column of the matrix. So what happens as when I try to compute the values in this column, I will realize that the values in this column, when I compute it in this way, are exactly P transpose X2. So I can do the projection by directly projecting the whole matrix, that is, all the columns of the matrix in a single operation by multiplying matrix P transpose with the full data matrix that I want, or contains the samples that I want to project. Okay, questions here? Okay, then once we have written a function, as I said, that given data and M returns P, and then in the solution online you have a function that given P and D returns the projected data, you can try to apply the solution to the Iris dataset, and you can see what happens if you try to plot the first two principal components. What does it mean? It means that you can estimate a P with the M equal to 2, so a solution of PCA which has two components. Then the projection will correspond to what? Will correspond to samples which have two components. Each sample will have two components, will be a two-dimensional vector because I'm projecting in a, so if I have x1, xi, let's remove I. If I have x, it gets projected to a two-component vector. If I select two dimensions, a two-component vector, I can plot it as a point in a two-dimensional space, scatter plot. So the idea here is project the points over the two first principal components, and then let's draw them in a plot. Let's plot the coordinates of the samples, of the projected samples. How? Well, since here I'm plotting on the x-axis the first component, so the principal component, the P1, and on the y-axis, P2. Now, one thing that we need to pay attention to, that we didn't say yesterday. You will, if you run this code, you may end up, and you can see it here because I was running it before for the previous class. If you run this code, for example, on this machine, you will get this image, which looks different from the one that you have on the PDF. And depending on the run, you may have even some things that look much more different. You may end up with solutions that look like this. For example, another possible image that you may obtain would have blue points, orange points, and green points like this. So this is something that you may obtain as well. Sorry, the blue points will not look like this, they will look more like this. Now, are these wrong or not solutions? Why, if you run the same code, if you run the code that I gave you on these four machines, you may end up getting there are four different solutions that you can get out of this. You may end up with four different solutions with exactly the same code. Now, why does that happen? And why is it correct or not? And why should I worry about that or not? Well, to understand what's going on, we need to go back to our PCA lecture of yesterday. Not yesterday, 1 week ago. And we need to remember what PCA is doing. To see what PCA is doing, let's consider, again, a data set. And again, let's imagine it's a two-class data set. The reason why we need classes is just so that we have points of different color. We don't really care what the colors are. I just want points of different colors to show what happens so that we can easily identify these points when we transform them. So the colors are just cue to see where the points end up. So imagine I have this situation, which from the point of view of PCA is unsupervised. It looks like a data set that is like this. Let's put the center here. Let's try to make it a bit more not exactly on the horizontal line because it would not look nice, but let's put it like this. So from the point of view of PCA, this will look like a set of points that are something like here. Now, what is the principal direction for this set of points? Remember that we showed that principal directions as a consequence of our objective, that is minimize the reconstruction error, the solution will be the principal directions, which are the direction with highest variance. So what is the direction with highest variance in that, for that data set? The vertical one has some spread, but this direction has the largest spread. So this would be the PCA direction P1. But let's not draw it like this. This is the direction P1. So the PCA would project the samples on that line, okay? Do we agree on this? Or do you have doubt? Direction with largest variance is where I want to project the data because I throw away the direction with lowest variance, so I minimize the amount of error that I make, because low variance means low reconstruction, low distance from the points to the corresponding mean. And the line here goes through the mean of the points in the opposite direction. So PCA looks for direction with large variance. But how can we represent this direction? We said we represent direction with a vector W. But how can we represent this direction? We can represent it with a vector like this, but we can also represent it with a vector like this, green and yellow. They both represent the same direction, we're just using a different orientation. So it's like representing the same axis, but when I represent an axis in the coordinate plane, I can put the arrow on the right, which is what you usually do, but I can put my arrow on the left. I'm still drawing Cartesian axis. These are axes. It's just a convention that the arrow should point to the right when you draw it. Do you agree on this? And here, again, I'm typically free to choose both orientation. There is nothing that says the yellow one is better than the green one as orientation. But let's see what happens if I select yellow and if I select green. Let's go back to the colored version of the plot. Let's project over this line, but, sorry, I wanted to do it black, using the yellow orientation, okay? Which means that if I see this as an axis that I project my samples on, this will be the origin of my axis. The red points will be where? Well, from the point of view of the axis, will be on the positive side of the axis. The red point will fall here, right? The blue points will be on the left of the origin, so they will be in the negative region of the axis. What happens if I plot on the green line? Again, let's draw it like this for the moment. The origin is here. In this case, the red points will fall here, and the blue points will fall on this side. If, as usual, we assume that the positive values are on in the direction of the arrows points to, this will get a positive value, the red will get a negative. What does it mean? It means that if I take this arrow and now I just move it here and draw it again so that the axis arrow points to the right, which is completely arbitrary selection. I decided that in my plots, the arrow should point to the right, my blue points will be here, and my red points will be here. And the value, if this was +1, this will be -1. If this was +3.5, this will be -3.5. Of course, assuming that the direction, the vectors W that I select are always unit vectors, so the norm of W is always 1. What changes is just whether it points in one direction or in the opposite. Essentially, I have W solution, but -W solution is perfectly acceptable. If the yellow one is W, the green one is just -W. It's representing the same direction, just with the opposite orientation. For us, we have no reason to choose one, so both these solutions are acceptable. Now, why you may end up with any of these, that's because, well, one more thing. What are these vectors? These are eigenvectors of the covariance matrix. We said for us these are equivalent, but this is just telling us something that we know. If W is an eigenvector of A, minus W is also an eigenvector of A, and it's associated to the same eigenvalue. So it's just one eigenvector that is parallel to the original W but points in the other direction. So even from the point of view of extracting eigenvectors, both are valid solutions for the first component. If W is a valid solution, minus W is also an eigenvector associated to the leading eigenvalue. So which one should I choose? We didn't say yesterday, but whenever we select the eigenvectors associated to the leading eigenvalue, we actually have at least two possible solutions that point in opposite directions. Which ones should I choose? Well, we never specified which one should I choose. We will use libraries that do not specify which one should be preferred. The libraries that you use will find one eigenvector. Which one? It depends on the implementation of the library. So on the numerical library that is actually used on your PC, on the architecture of your PC, because in the way these eigenvectors are extracted is through numerical procedures. Different architectures may end up with different approximations of some computation that may end up giving you the different sign for the eigenvectors. Remember that our eigenvectors are always eigenvectors up to some precision. They are not exactly the mathematical eigenvector. They are numerical approximations of the eigenvector. Which numerical approximation I get may depend both on the algorithm that I use to compute it and the machine that I compute it on, because different machines may need different approximation because of just the machine precision or the architecture of the CPU. So I cannot tell you in advance which solution you will get. From our point of view, whenever we don't say anything, it means that all these solutions are equivalent in the sense that what we do with the data afterwards will not depend on the directions that we take. So for us, all these solutions are perfectly acceptable and are equivalent. We will see next week that when we use LDA for classification and we want to cast LDA as comparison of a projection with a threshold, then in that case we will need to specify which direction we should take. We've discussed yesterday already, but we will recall it next laboratory. In that case, and that's the only case, where we will need a specific direction for our code, for our algorithm to work, we will specify how to select, to decide which is the direction, which is the orientation that we want. For all the other cases, we don't specify it, and you will obtain different solutions that for all the other purposes are equivalent. So they are correct. You may not get the same plot that you have on the slide, on the PDF. You may get different plots. The difference is that your plot may be what? May be, let me take it, may be flipped over the horizontal axis. So it may be flipped according to this axis. It may be flipped with respect to the y-axis. It may be flipped with respect to both. And whenever you see a flip, you will also see that this corresponding value will become minus the values that you have here for the same points. So if the plot, for example, is flipped on the vertical axis, your points will end up looking like blue orange, sorry, no, let's flip it correctly. Look like this, then this for the orange, and then this for the green, and here you will have values that will go from minus 4.0 to up to minus, sorry, from minus 4 here up to minus 6.5 here, because we always point upwards, so they increase. So your values will be the flipped version of these values with a negative sign in front. Again, I cannot anticipate what you get, so know that you may get exactly the figure that you have there, or you may get even both axes that are flipped. Okay, questions? Okay, so this is the PCA part. Then for LDA, we didn't discuss LDA, but we can bring ourselves a bit farther for next laboratory. We know that for LDA, we will need to compute between and within covariance matrices. This we can already, even if we didn't see how to use them, we can already start computing with what we learned. It's just a matter of reorganizing our data to compute those expressions. For the within class, it's explained in the code. You can essentially reuse the code that you have for computing a covariance matrix of a data set. It's just the within class, as we find in text, can be expressed as a weighted sum of the covariance matrices of the samples of each class. So it's a matter of splitting the samples over each class, computing the covariance matrix of each class separately as if it was a single set, and then weighting them together and summing them. The between is a bit more complex, but a naive implementation of the between is not difficult because it's just a matter of doing 3 vector-vector multiplications, each time weighted by a value that is the number of samples. So we can do it with a simple for loop. It's just a matter of computing the correct values here. So the idea here is, I expect that you should be able to run the PCA, and hopefully some of you may also be able to do the first part of LDA up to the point where we compute these matrices. The rest we will do it in any case next week. Okay? Okay, you can work. If you have questions, of course, I can come to you, or you can come here. We'll just comment on what you find online. Yes, solution for this, just to say a couple of words on this, not necessarily different, better than what you did, but you have a file where we solve the PCA parts of the project, of the laboratory. We first have a load function for the data, so this is the same from previous laboratory. We defined it last week, the version where we load it from the library directly. Couple of functions, we already introduced them last week to reshape a vector as a column or row vector, and then functions to do the steps that we need. The first, compute mean and covariance. Put them in a function because the suggestion is do that because we will really reuse them. Well, for LDA, you already seen that you need to do the same thing. We will reuse them several times. So a function that given a data set computes the corresponding mean and the corresponding covariance matrix. How? Well, how we have already seen last week. We use mean to compute the mean. To compute covariance, we use the definition of covariance. Notice that depending on how much you look, you may have seen that there is a cov function in NumPy that we didn't introduce. Now, don't use that. We said that we can use that for standard deviation, for variance, and for mean. There is one that computes C, but if you use cov directly, it will not give you this value. It will give this value computed with a 1 over n minus 1 denominator, which is not the empirical covariance matrix. There is a reason why it does that. You can pass parameters to force it to compute the thing that we need, But to avoid confusion, just don't use that. It's already a Python exercise, NumPy exercise on its own to compute it, to compute the correct one. So we do it manually so that we both see how to use NumPy and we're sure that we're getting what we want here. Does it change if you use 1 over n rather than 1 over n minus 1 when computing the covariance matrix? For PCA, it does not, but for other tasks, it would change the result. So we cannot use cov directly because it will not give us what we expect. When we use it, we should either force it to give us the empirical covariance matrix or know what it's actually computing and using it in a proper way. This is just a parenthesis. So we compute explicitly our covariance matrix, and then we return them. Then the function that computes the PCA, it receives the data that will be used to estimate the PCA matrix. So the model is trained on this data D, and M is the number of directions that we want to keep. First step, we compute the covariance matrix. We return also the mean. We won't need the mean, but the function needs to compute the mean in any case because we need the mean to compute the covariance. So we have the mean for free here. We will just throw it away. Then given the covariance matrix, here we use the SVD solution. We know that the SVD solution will give us the eigenvectors, the principal components as the first m columns of matrix U. So we just select those and we return them. Then a second function that, given a trained model, will apply that model to some data matrix. It will simply compute the product for all the elements. This is the non-loop version that we saw in the laboratory. This will take our matrix D, which will contain columns, and the result will be equivalent to computing P transpose X for each column X of my data matrix. This is exactly what it's doing here. Now, what you have online is a solution that stops at the point where we save the PCA with 4 dimensions. And it's saved in this file so you can load it from the file. Remember that the PCA with 4 dimensions will contain all the eigenvectors. So the PCA solution that you will get with m equals to 3 should be equal to the first 3 columns of this. If you set m equal to 2, you should get a solution that corresponds to the first 2 columns of this. If you set m equal to 1, you should get a solution that contains only the first column of what you have online. So you can load this matrix that you find in the material section. Then m equal 4 is exactly this matrix. M equal 3 is the first 3 columns of this matrix. M equal 2 is the first 2 columns. And m equal 1 is given by the first column of this matrix. What you're asked to do afterwards is not in the example here, but it's fairly easy. We said, let's take, and I will comment this because I didn't download on this machine the file, so I will just say that the file is not there, but you have it online. If you download it and put it in the same folder, it will run. We said, let's compute the solution with 2 components. So we select the solution with 2 components. And then we want to do the scatter plot. So we create our figure. And then we we project our points. How? Well, we use the apply PCA function. Now I don't remember whether it was P or D, first P. And in this case, we said the data that we plot are the same training data that we use to estimate the PCA. So it's always the same iris dataset, the full dataset. Then next week, we will split it into 2 parts, and we'll explain why. Now, this DP contains what? Contains is a matrix 2 times 150, which contains the projection over the first principal component as the first element of each vector. So each vector is a 2-dimensional vector. The first component corresponds to the projection of the first principal component, and the second component is the projection over the second principal component. So we use these as if they were x coordinate and y coordinate of a point to plot. How do we plot it? With a scatter plot that receives the first coordinates as x coordinates of the samples, and then the second argument is the vector with the y coordinates. So we call scatter, and we pass the first row of the matrix, which contain the coordinates that should be used for the x-axis, and the coordinates for the second axis. If we show this, it will look similar to what we have, but not exactly the same, because we will get a single plot where all the points are blue. That's because I was doing a single scatter plot. If we want to have the three colors, we just plot one after each other the points of each, the scatter plots of the points of each class. So for each class, we select, as we did last time, the points of that class, and then we run this code, we will get the colored version of the plot. Now you can see here that what I get as output is not what I have in the laboratory text. In the laboratory text, I had the plot where the horizontal axis has negative projection values, the vertical axis has positive values. Here the x-axis is the same, but the y-axis is flipped. Indeed, you see that it's a flipped version of the image. This is exactly what I said before. For the second principal component, this machine took the opposite direction with respect to the one where I generated originally the plot. The original plot was generated on a machine which took the principal direction like this. Here, the principal direction was taken to be the opposite of the one that I selected. And indeed, you see that the numbers here are negative and the points are flipped. Okay, questions up to here? Okay, this is the PCA part. For the LDA part, I will go back to that next week. What I want to say is a couple of words on the project part for the PCA. So the one that you have to do at home. You are asked to apply PCA to your data. And for the moment, to simply train PCA over the whole training set, apply it to the same training set and see how it would change your data. Then this is the first part. Then after we start using PCA as preprocessing for LDA, we will see that we will learn PCA from a subset of the data, but we'll explain this next week. For the moment, we just train PCA and analyze what happens, as we did with the ARIS dataset, when we train PCA and we apply it to the features. In particular, here, you are asked to plot the histograms for all the 6 principal components in order, and then plot scatter plots for the different feature combinations. That is, for the moment, we don't reduce the dimensionality, but we see what happens along the different directions that PCA preserves. We know that if we set m equal to 1, we will get only the first principal. If we set m equal to 3, we will get direction 1, 2, and 3, and so on. We analyze what happens over all 6, knowing that whenever we select an m, we will be selecting a subset of all of those dimensions. So for visualizing what happens, let's look at them, knowing that when we select a subset, it will be a subset that goes from the first up to the mth one. Now, one thing that I would like you to observe is what happens to the histograms, and then to reason to what's going on really. You will see that there are differences in the distribution of the features with respect to what you observed in the previous week. What I would like you to observe for the moment is, remember that PCA, when I keep 6 dimensions, before I select which subset to take, so when I look at all the directions, it's actually just doing a rotation of my data. this rotation, then if I want to reduce dimensionality, I will keep only the first m components of the rotated vectors. But as long as I do the analysis of all the directions, I can interpret this as a simple rotation of the data. You will see that some of the considerations we made from the scatter plots last week will look like they changed. I would like you to reason on whether these changes reflect for real something that has changed in the way the samples are organized, or if it's just an artifact of the fact that when we apply PCA, we rotate the space. So when we do plots of histograms and scatter plots, we are observing the data from some directions, essentially. So reason whether what you see can be really justified as changes in the data, or it's just an artifact of how we visualize the data. Remember that we never do 6-dimensional plots because we can't do 6-dimensional plots. Every time we do a histogram of a scatter plot, we're doing a projection of the points on a plane, like when you were doing projections in high schools. You know that if I change the plane I project, I will see things differently. So some things that may be apparent when I do the histograms in the original features, when I rotate my samples, may disappear. But did these things really disappear? It's just a matter of the fact that I'm looking at the samples from a different point of view. So you should reason on this. And we will see next week.